It's join. Yeah, so recording has started. Okay. Yeah. So good morning once again. Um, and welcome to this class. Right. In the last class, that is in the last week, we were discussing about this propagation delay, right? And while discussing this propagation delay, we have found that this delay, basically in case of the CMOS inverter, there are two components like any other delay. And we have seen for the first order analysis, we can represent this delay by using an RNC, first order RNC system, right? So where this R is offered by the on resistance of this PMOS during charging, and the capacitance is primarily the load capacitance as of now. So we'll also see that there are some component, means some capacitive components of this PMOS and NMOS will also be attached along with the CL. So all those things we will see okay gradually. But as of now, we are considering that the CL is quite high, this capacitance, and the major load okay of this at this output is due to this capacitive load only, and so the main delay is primarily due to this R and CL, right? So now, as you have understood, this R basically has means the resistance of this, right, on resistance. Similarly, for discharging, this R would be the resistance of this NMOS, and we will see that how can we estimate. It is basically you know how to estimate, but type of approximation, what approximation we can take to calculate it this resistance quickly for hand calculation. Okay, so but for in today's discussion, we would like to see what are the capacitances okay that are associated uh, here. Like if you consider this CL, means this say this inverter is driving another similar type of inverter, then obviously you would have connected one here, one PMOS, and here one NMOS. Right, then what would be the capacitance? Is it the only capacitance which is due to this gate capacitance or something else? That we should also see. Okay, so that is the main objective for today's class, and we'll see that okay how far we can complete for this on this topic. Okay, so this is MOS structure capacitance. Capacitance in a MOSFET, right? So here, whenever I say like MOS capacitance, so the primary thing that would come to your mind, hopefully, is this gate oxide capacitance, right? Gate oxide capacitance, where we have also seen it during our expressions, like whenever we were writing this current expression, ID expression, we have this COX terms, right? And this COX is primary, this basically this C epsilon ox by TOX, right? Where you remember this epsilon ox is the dielectric constant, of silicon dioxide, right? And please do remember this value. Sometimes it is useful. This is 6.9 into epsilon naught, right? So this is equal to this 3.9, right? So please do remember this value. This is 3.9. Okay, this is for silicon dioxide. Okay, SiO2. Now, in this context only, we will see that later on why we use this high K dielectric, where this K value here means the relative dielectric constant will be substantially higher. Okay, for example, if you are using hafnium oxide, okay, HFO2, then it would be more than 20. And there are some advantages and why we have to use those high K dielectric in the next generation, or yeah, need for next generation MOSFETs, that also we will see. But one clear thing that you can understand, means one obvious thing that you can understand from this expression only, that to have this COX higher, why we need COX higher? Because we know this ID is proportional to COX, right? So to have higher ID or to have a better gate control, you should have this COX to be also higher. So to have COX higher, obviously you should have this TOX lower, right? But there is a minimum limitation till which you can actually lower this TOX. You cannot go to it too extreme, because then otherwise gate leakage would be an issue, right? Okay, So in that context, you can just also guess that there would be another possible way that you can also, there is a possibility that you can increase this epsilon ox, right? You can reduce it, but at the same time, you can also increase the Cox. That way also you can have this Cox higher. So that is the main motto why we need this high K dielectric. High K dielectric, right? For example, it is hafnium oxide, right? And that's why this hafnium oxide is being introduced in the later part of this MOSFET, and why this hafnium oxide still is being used. Okay, right. So now this is one of the capacitors. Yes. Do you have any question? Okay. No. Fine. So then along with this gate capacitance, we have some other capacitances. So let us discuss those things. First thing we will discuss this on overlap capacitance. Okay. So what do you mean by this overlap capacitance? Just it is very easy. Just draw this structure, MOSFET structure, and you will be able to understand and or explain it. So say we are using this NMOS, right? So that way we have this source and drain. So let us say that this is source, this is drain. And obviously you have noticed one thing, whenever you are making this source and drain, right? And you are putting gate. So this gate is always been overlapped with source and drain, this N plus and N plus region, right? I hope you have noticed that. And there is one technological reason as well why we have to do it. I think those part we will take off when we are discussing the fabrication part. That why we should have at least this much overlap. Okay. And so this is the oxide, right? And this is the gate. So this is gate and this is oxide. So this is SiO2, right? So whenever we are saying Cox is basically the capacitances which is associated between this region, right? So like you can say this is one terminal, and if you say the other terminal is the body, right? Then the this one plate is this, right? And the other plate is this one, right? P silicon. So the capacitance between these two is this Cox, right? But you can think actually this is the actual gate. Actual gate means the effective gate, right? And this is your physical gate, isn't it? So this is the physical gate, right? And this is the actual gate length or the effective gate length, right? And you can clearly see this much is the overlapped regions, right? Let's say that we will term it as XD, right? So this is what cross-sectional view, right? This is the cross-sectional view. Let me write that as well. Cross-sectional view, right? If you think of its top view, then how does it look like? That would be interesting to note from this top view. So you should also notice that here, this we have drawn it in a two-dimensional way, right? There is actually one more dimension, right? Like this, no? So you could have drawn it in that way also, three-dimensionally, right? Now try to think that if you are looking from the top, how does it look like? Then it basically looks something like this. Let me choose the same color, like pink. Pink we have used for this gate. So say then this is that gate part. You understand? This is that gate part. And here inside that you have this source and you have this drain. This is drain N plus and this is source N plus, right? So clearly we can see from here that there is this portion, this is the capacitance, which is not a part of the gate capacitance, right? And this actually, if I have to also term it like as we have done it here, then this is basically that XD, right? This is XD. Okay. And if we consider the actual length, so this is L dash, so this is L dash, and if we say like the width of the transistor, say this is the width, then width is this one, right? This is the width of the transistor. Even though you can see the gate here is extended much more region, but the width, if you say the effective width is actually this one, right? It is actually the width of the source and drain regions, because only for this region you have this channel, right? The current can only flow from here to here. So even though the gate is extending beyond that, the current cannot flow through this, through that region, right? So current is confined only to this region. So this is the effective gate width, effective gate width. So this one is that way, right? Okay, so this is that overlap capacitance, right? Okay. Now, can you understand, means do you understand why this will happen? Any idea? Any idea from any one of you? Like why there should be an overlap, XD? Who can answer? Arsh, can you answer it?
Sir, I'm like thinking, I was probably thinking that the channel would not form in that triode region,
Okay.
probably.
So yeah, actually, this is one of the, one thing probably you have actually done it in your devices laboratory course, that when you do some diffusion, right, means you have done some diffusion, make this N region, right? Make this N plus region by diffusion. Then after that, what you have to do, and then after that, you have to heat it to reduce the damages here. So when you heat, then what will happen? The same thing, okay, the dopant will diffuse further. So say this is the earlier dopant profile, but now after heating, the dopant profile will be somewhat like this. Okay, so this is called the lateral diffusion. Lateral diffusion is this one. Similarly, there is one diffusion along this side, right? So this one I am referring to the lateral diffusion. So due to the lateral diffusion, on this part, this N plus region will come under this gate. Okay. Now, is it important or should we have it? And the answer is yes. If we do not, suppose if we make it, if you make the gate something like this, huh, and after this, even for the after this lateral diffusion, if the gate is forming, okay, I hope you are getting right. This gate is on this side, right? So you can see there is some region which is not been covered by gate and also not been covered by the N plus region. So in this region, gate has no control, so the channel will not be formed here. So the effect total channel will be disconnected from this drain or source side. Right, so that way you will not have any current. So remember, for this type of devices, you should have, only for this type of devices I'm referring to, you should have an overlap between this gate and drain and source regions, right? But is it intended? Actually, the thing is no, because that creates this type of overlap capacitance, which is not an and good thing for us, because see, the gate capacitance we need, because the gate capacitance, depending on the gate voltage, we can control, and that basically creates the channel. But these capacitances, right, is always there if you have considered gate control or not. If these capacitance are always there, and this type of capacitance always behave as a stray capacitance, right? And it is very easy to like estimate this type of capacitance. So if you are considering for the source side, we will write it as CGS naught, right? And if you are considering on this drain side, it will write it as CGD naught. This naught or O is referred as this overlap. This stands for overlap, right? So this would be. Can anyone help me? Like how can we express? like based on whatever we have discussed? Ayushi?
So would it be epsilon of oxide divided by
Epsilon of oxide by
epsilon of oxide multiplied by the area? The area would be
multiplied by
width of
area would be the width, that is W.
yes, W source and I mean the overlap of source and gate.
Overlap, so that is the XD,
Yes,
right? Okay. And what else? Are we not missing something?
divided by the thickness of oxide.
Divided by the thickness of oxide. Very good. So is it not like this part is not this COX? It
Yes,
is, right? So basically then we can we not write it as like COX W into XD, right? So you can see then this GS naught, that is gate to source overlap capacitance or gate to drain overlap capacitance, can be written simply if we know the COX and if we simply know this XD, right? Width we always know because width is the thing that we will design as a designer, but we should only know that what is the XD value. So if we know the value of XD, we can calculate what is the overlap capacitance here, right? And we can always see from here that this is of fixed value, right? Fixed value. Fixed value in the sense means, is it like dependent on the gate voltage? The answer is no. It is not dependent on the gate voltage, right? And it is linearly proportional with the width, right? This CGS naught or this CGD naught is linearly proportional to the width. So you make the width higher. At the same time, your stray capacitance, this overlap capacitance, will also become higher, right? And here, one more thing, that this double XD is also a technology parameter, and this XD is same for both source side and drain side because this MOSFET is a symmetrical device, and fabrication is also this type of symmetrical only. So that way, we do not, when fabricating this MOSFET, we never consider that this would be the source or this would be the drain. You can always interchange them, right? So that way, XD would be same for any technological node. So if you know that XD, then we can always consider and write it as CGD naught. This would be equal to C naught into W, where this C naught is equal to COX into XD, right? So if it is so, can you please tell me then what would be the unit of C naught? Ayushi? Ayushi? Ayushi Sharma.
so it would be
Hmm.
capacitance divided by length, right?
So it is basically then the cap per unit length, right? Isn't it?
Yes, sir.
Okay, nice. So this is
Sir, I have a
about,
doubt.
right? Yeah, please.
Sir, why is the capacitance CGSO is epsilon OX WXT by TOX, sir? Like the area part, why is it W times XT?
Area is YW times of XD. Okay, that is because like this gate, right? And what is the overlap area? So is it not the overlap area? Like,
Yes, sir. But
huh?
sir, the current is flowing from source to drain.
Right. Current is flowing from source to drain. So current boundary is here,
Yes, so
right? Like
sir,
this.
uh, so the area of cross section it is facing.
Huh. No, you are seeing this capacitance, right? So you think about from here, right? Maybe if I can, so show it from here. So you think for this region, right? So this is one plate for this overlap capacitance, and this is another plate. This is another plate for this capacitance. So the capacitance is between this one and this one overlap, right? So this would be the area, na? So this is the XD and this is the width.
Okay, sir. So it is basically the capacitance between source and gate.
capacitance between, yeah, between gate and source, right? Between gate and source, overlap region.
Yes, sir.
Ah,
Got it.
Overlap region, right? And so, so you can always see this, that this capacitance will always be present, right? Even the capacitance in the cutoff means the MOSFET is a cutoff. It is the same value, saturation, triode for any region of this MOSFET to be, right? This capacitance will always be the same, right? Okay. Then now we have considered about the gate capacitance, right? We have some idea about gate capacitance. So you'll also see that this gate capacitance means what? Okay, maybe I can show you the brief discussion. I can do it from here and then do it. See, what do you mean by gate capacitance? Gate capacitance is between gate and what? What do you mean by gate capacitance? It is between gate and what?
Channel.
Gate and channel, right? So where is the channel? Here. Channel will from here, right? Okay. So suppose the device is in cutoff, then there is no channel. Then what will be the capacitance? Then the capacitance would be between the gate and body, isn't it?
Yes, sir.
Right. So that way we can say that this channel capacitance, which is actually the most significant capacitance, this is actually the most significant capacitance in MOSFET, right? Because whole transistor operation depends on this channel capacitance, right? And so this is denoted by this, this CGC, gate to channel capacitance, right? And gate to channel capacitance can be divided into three, three different capacitance. One is CGCS. I will write them first. CGCD, and the other one is CGCB. So this is the gate to channel capacitance component, which is actually between the fed between gate and source. Remember, this is not the overlap capacitance. This is the gate to channel capacitance, the component which would be feeding between this gate and source. So it is between gate to source. This is then, from the same token, we can say this is between gate to drain, and this is between gate to body, right? Now quickly let us discuss three different scenarios and try to understand what do we mean by these three components. Okay, so I will make one MOS structure quickly, and then I will copy it 3 times. Again, we are considering NMOS. So if you want, you can always do the same thing using P-channel MOSFET. This is source, this is drain, this is oxide, this is metal, this is gate. Okay, now let me copy this image for 3 times. Yeah, now let us discuss 3 different scenarios. First is the cutoff, right? So this scenario is for cutoff. So when you have a cutoff, that means the gate voltage is below the threshold voltage. Say you have not applied any gate voltage, right? Here, say the threshold voltage is 0.5 volt plus you have applied gate voltage equal to 0, right? You do not know what is the condition of source and drain as of now. Obviously, the source is grounded, and drain voltage, say you have not applied anything in the even in this drain side right now, right? Then what would be the capacitance? Then the entire capacitance, this CGC, would be between this gate terminal and this body terminal, right? Because body terminal, this is connected. So here, this is the whole potential. This will be at the same potential, right? because there is no current, so there will be no voltage drop, right? So the same potential here. So you can say like this is one plate, right? And this is another plate, right? So that way the whole capacitance would be between these two, right? Okay. So you understand here, this is between CGC. So the entire thing would be fall between this gate to body. So it is between gate and body. Let us take the next case, say the resistive region or the triode region. So in triode region, you have applied say 1 volt at this drain terminal, and you have applied and say the threshold voltage is 0.5 volt, and you have applied suitable drain voltage such that the diode, this transistor is in the triode region. So the triode region means that there will be channel, and the channel will be connected from this source to drain terminal, right? So this is the electron channel, and it has been connected right from here. Now you see, whenever the channel forms, right? You see here, whenever the channel forms, this electron, okay, this electron layer will create a shield between this gate and body terminal, which was present here, right? Between this, right, with gate and body here, because there was no channel. So as soon as you have the channel, right, it will start the shielding between these two. So now your gate to body, that component CGC would become equal to 0, right? I hope this you have understood, right? So this is electron, right? This is actually this electrons, right? And these electrons are connected with N plus, and here also it's connected with N plus. So this gate to channel capacitance would be equally divided. That is CGC would be equally divided between this gate to source and gate to drain. So that means if we have to draw it in a simplified way, you can say this would be divided between source and drain. So it would become half of CGC. So here half of CGC, right? Because connected between these two. Okay. So this is in triode region. Now let us see what will happen when the transistor is in the saturation region. So I hope that you remember from your semiconductor device class that when the saturation occurs for this type of long channel MOSFET is due to the pinch off, right? So pinch off has occurred. So that means this electron is not been, or the channel is not been connected from source to drain. So the channel is always connected with the source, but now it has been disconnected from the drain side. So the channel looks somewhat like this. The channel has disconnected from the source side, but still this channel would be able to disconnect this gate and body. Disconnect in the sense all the electric field from here would be terminating here. So this gate to body component, that capacitance would still be equal to 0. But earlier this capacitance, gate to channel capacitance, was equally been divided between source and drain. Now you can see this electron channel is only connected with the source. So this gate to channel capacitance now will be only appearing between this gate to source. So the gate to drain component of this capacitance would become equal to 0. So if we have to draw it this way, then it is between gate to source, and it would become C of GC. Now, what would be the value? Total value, is it become the total entirely equal to this COX? Actually, it is, and the answer is no. It would become the 2/3 of maximum value of CGs. Okay, if you do some rigorous analysis, so it will see that it will become 2/3 of this CGC, right? With some approximation, obviously, right? And the drain component would become equal to 0, right? Now, if I may, from this, try to plot this after this. Okay, could you please guide me? This, I want to plot capacitance, and here it
Sir,
is.
can you please repeat why for the third case? I mean, in the saturation case, CGCB equals to 0.
Yeah, why? For the last
Third
case?
case,
Last
gate to body is 0.
Gate to body is 0. Okay, so here means okay, have you understood like why it would be 0 for the second
Yes,
case?
yes, yes, sir.
Right. So you are still, you might think that, there are some regions right here.
Yes, yes.
Right. But actually, we are saying the channel does not exist. But how do you define channel? So there will be always some or some amount of electron here, and those
Yes.
electron would be will be sufficient enough to terminate the electric field which are coming. Say we are applying positive voltage here, na, positive, na. So this has to be terminated in some negative charge, right? So this would be able to terminate here. So nothing will come for
Okay.
this place. Okay, so that way it would be like the entire thing will be fall across this part only. Okay.
Yes.
So if you have understood this thing, and let us also see that whether you have understood or not, then if you have understood, then you will also be able to guide me, okay, in this case. So say we want to plot this capacitance, the entire capacitance, this gate to channel capacitance, gate to channel capacitance versus this VGS, okay, when VDS equal to 0. So remember VDS equal to 0, source is already 0, so you are now also grounding the drain terminal. Okay, now could you please tell me when this 0, three components we will draw, right? So three components we will draw. The first one is this CGCB, which will green line. Then we will take this CGC source, which we'll use for pink line, and this CGC drain, which will use the blue line. So could you please guide me how these things will look like? So let us discuss what will happen when this VGS equal to 0. Maybe who want to tell? Shubhayan, you want to tell? Shubhayan?
So then the cutoff region.
Yeah, then could you please tell me what will happen? Just tell me at what will happen at 0 volt. What would be the value of CGS and CGD?
Okay. P naught into W.
No, no, no. This okay. This capacitance
They will
is
not.
this
Yeah.
capacitance is CGC. This capacitance is CGC. So overlap capacitance will not, we are not considering here. Okay,
Okay.
overlap capacitance we have like explicitly mentioned here. Then finally now we are discussing the each and individual component of capacitance present in MOSFET separately. Finally we will include them together. Okay, so this is separate discussion. Now this channel capacitance is a separate discussion. Yeah, please tell me what would be the value of, okay, tell me what would be the value of CGCB?
Sir, CGC.
CGC. Okay, what will be the value of CGC maximum? CGC max. What would be the value? Yeah, can you please tell me from here? CGC, what would be the maximum value? It is L dash into width. This is L dash, right? Into width
W epsilon
into
naught.
Cox. So please check. Have you understood why I'm writing this? CGC max. Simple, right? It is always be Cox, right? Because we are considering this structure. Always Cox. Now you have to also consider the area. This is the L. This is the physical gate length. So, but you know that physical gate length will not be equal to the effective gate length, right? Because you have to consider the overlap region. So overlap region you have to reduce. So without overlap region, you have this L dash region. So it is basically L dash W into Cox. So then, okay, let me choose this one. So it is Cox W L dash region. Okay. So this is the value of CGCB. What is the value of CGC here? CGCS, pink component, and this component? 0. So anyway, they are here. Okay. So now we were increasing this one. Okay. Now we are increasing this gate voltage. So what do you think it will happen to this CGCB? Please try to understand what I'm saying. Earlier you have put
It
0
is
voltage
on.
here, right? Now you have put 0.1 volt. Now you are changing to 0.2 volt, and threshold voltage is 0.5 volt, right? We have not reached threshold voltage, but we are just increasing. So what will happen if you increase it?
Sir, the CGCB will decrease.
CGC will decrease. Why? Yeah, why it will decrease?
So like I was kind of following the spectrum, and I found that in the triode region we don't have any capacitance between gate and body. So I mean, the changes cannot be abrupt, right?
Okay. You
So
are saying from that perspective, but
yes,
what
sir.
from the semiconductor physics?
The electrons will like come closer to that.
No.
So
No,
as
no,
we
it should
the
see
PGA.
in MOSFET it does not work like this, right? You have 0 volt, fine, right? You have this P region here, fine, right? Then you make it 0.1. What will happen? So what are the majority carrier in P silicon? Holes, right? What are the majority carrier? Holes, na? Now you have started giving here positive bias, right? What will happen? These holes will repel, right? So holes repel somewhere bit region, right? So from earlier hole was distributed equally, but now the hole has been repelled from this region. So that means this region is called the depleted region, right? So depleted region is equivalent to this dielectric layer. So that way the separation between this gate and this body has now increased. Don't you know this thing? Then you change to 0.2, it will further extend. Now until and unless your gate voltage is equal to 0.5, this will keep on extending. Once you have this 0.5, that would be the maximum region, depletion region. Say this is the maximum depletion region. Then after that you increase, say 0.5 to 0.51. Then after what will happen, electrons will now be attracted and electrons will form here. So that is called the inversion. So once you are increasing the gate voltage and going towards threshold voltage, so what you are basically creating, you are creating a depletion region. Inversion region has not been created then, right? Inversion region means the channel has not been formed, right? So until and unless you are reaching this threshold voltage, your channel would be keep on, means the semiconductor will be keep on depleting. And so that way, what you are getting is basically the separation between this gate terminal and this body terminal is actually increased. So earlier it was separated only by the oxide, but now it has been separated the oxide plus this thickness. Please tell me if it is not clear to you. Arsh, is it clear to you?
Yes, sir, it is clear.
Okay. So what about Avik Datta? Avik, is it clear to you?
Yes, sir.
Okay, fine. So we understood from here that as the separation has, separation will keep on increase with increasing VGS, right? So this one CGCB will be falling, right? But what will happen to the CGCB? But CGCB still that channel has not been formed, so still we can expect that value would be very low, close to equal to 0. So let us mark then one point where we say that this is the threshold voltage. So this is the threshold voltage, right? So we have seen from here that until this got restarted. This Windows. Hopefully, I will be able to. 1 minute. Let me restart it. Hopefully, some of the things would be saved. Yeah. Fortunately, it is saved. Yeah. Please check it once. Is it visible? Is it visible? Okay.
Yes.
Fine. Okay, fine. So let us say that this is the threshold voltage. Then we have understood like till threshold voltage, this will fall, right? And at threshold, so at threshold, what will happen? Your channel will be filled. Means channel will be formed completely, and then after that, we know that there will be no CGCB component, right? Okay. Then after threshold voltage, what will happen to the value of this CGCS and CGCD? So that also we have seen from here that CGCB and this would become equal to half of Cox W L dash. Right. Similarly, this one, the blue one, would be also the same pattern. Right. And if you further extend it towards this side, it would take, this type of form. So why you can ask this question, like why this should not start from here? Actually, this inversion does not happen all of a sudden, right? Electrons will be start accumulating from here, even prior to this oxide, prior to this VTH. Okay, but VTH is the point where we consider there isn't complete inversion, right? But all of a sudden nothing can happen, right? Because it is, you can see that electrons the concentration will be increasing, keep on increasing, but it will be slow for that region. Right? So that way here also it will follow the same thing, same pattern, right? And if we have to plot the total capacitance, total gate to channel capacitance, then probably it would be something, it would be somewhat like this. Total CGC, total gate to channel capacitance, right? But consider, please keep in mind that we have considered VDS value equal to 0 here. Okay, right. So is this part clear to you? Like how this transistor would behave, the capacitance would behave, get to channel capacitance when there is no VDS. Now let us consider we have also applied VDS. Maybe it would be better if we can do it here only.
Sir,
Huh.
can you show that how the CGCS is formed? Where does the field line?
CGS has how this has formed. Okay.
Yes, sir. So where does the field lines go?
Okay. So so the field lines would be, say these are all negative charges now, right? And these are positive charges, right? So it will be actually, this straight line only. Okay, but as this is part is connected with this part, so you can say that half of this is associated with the source and half of them is associated with this drain. Okay, so now let us consider the non VDS. VDS is not equal to 0, right? So that means we are considering something, we want to plot it like this. So this is a type of generalized plot, and I think you can understand why I am plotting this one. So I am plotting here VGS by VDS by VGS minus VTH. Okay, so can you please tell me why I am plotting this? What do this x-axis signify? When the transistor will reach to a saturation region?
At 1.
At 1, right? So that means this, when you cross here, then this region is basically the saturation region, and beforehand, right, beforehand, this region is the triode region. Beforehand means from here, right? This is the triode region, right? So if you understand from here, and we also know what is the maximum capacitance, so the important things are WL dash or Cox WL dash, this one, and the other one is half of Cox WL dash, right? And we have seen finally it will reach to 2/3 of CGC, right? So say this will be somewhere here, like 2/3 of Cox WL dash, right? So could you please now then tell me again, say like from, we are basically doing all the things here, right? Okay, so we want to plot all three components here as well. Yeah, please tell me what will be the value of CGCB. Can you show CGCB here?
So it will depend on VGS.
It will depend on VGS. Very good. So we are considering here VGS is greater than threshold voltage. Very good. So we are considering VGS greater than threshold voltage. Yeah. Now please tell me, if this VGS is greater than VTH, then obviously CGCB, this part is not present here, right? Okay. So we have left out only these two components, CGCS and CGCD. Okay. So please guide me. How should I plot CGCS? How should I plot CGCS? CGCS will change from half of the maximum value, right? Half of C ox WL dash, right? This become half, and this is the saturation, and at saturation it will reach to this 2/3. So it will reach to 2/3, right? Okay. And the other one is the blue, CGCD, right? CGCD. So CGCD we have seen from here that here this value would be half of this. So it will start from here, and finally we have seen when the saturation, this channel is being disconnected from this drain end. So this value would become equal to 0. So it will reach here to 0, right? So finally, if I have to plot the total capacitance again like this, CGC, then the total capacitance probably I can draw it like this. So it is CGC, this is CGCS, and this is CGCD. I hope this makes some sense. Yeah. Then we can you can see from here. So depending upon the region of operation as well as the voltage between this VGS, VDS, this total gate to source capacitance and all these components will keep on changing, right? But for our analysis, okay, to simplify our analysis, or okay, and for hand calculation, we will divide like explicitly 3 regions: cutoff, triode, and saturation region. And we'll say like if we have the cutoff region, then this value is fixed to this, and if it is in the resistive or triode region, then this value is fixed to this. Okay, so let us make a table for that, so that it would be easier for us, which will be a guide for us, to consider like what should be the capacitance we should consider, okay, at different regions. So we will first write here this operating region. This operating region. Then here we will write the first component, which is CGCB. Then the second component, CGCS. Then the third component, CGCD. Then here the total component, that is CGC. Okay. So here, if we write the first one, that is this cutoff region. Then in cutoff region, we have seen the entire capacitance is Cox WL dash will be only this value only, right? This value is 0, this value is 0, and this value would be that. This is, I have to just total it out. So it is Cox WL dash. Then the second region is the resistive region or the triode region. Triode region. So in triode region, we have seen this part would become like triode region. Obviously means we are here considering this VG is greater than the V threshold voltage. The transistor is on. So this component would become 0. So obviously in the other region, that is in the saturation region also, we know this would become equal to 0, right? And here CGS, we have seen this would become half of Cox WL dash. Here it would also become half of Cox WL dash, and the total capacitance is equal to Cox WL dash, right? And when it is in the saturation, then we have seen this CGS would become 3 of Cox WL dash. This would become equal to 0, and so the total capacitance would become Cox WL dash only, right? So then we have seen like how these capacitances are behaving, and if you know the region of operation, then you should be able to find like what would be the what would be the expected gate to source means gate to channel component capacitance would be, okay, for a MOSFET, right? So just to a BK recap, so we have considered so far these two capacitance. One is the overlap capacitance, which is because of this overlap of this gate source and gate to drain. Then we have seen this gate to channel capacitance, which we already know, but we have seen that this capacitance can be splitted between gate to body, gate to source, gate to drain, and we have also seen how this, how you can actually find these components, right? Okay. Now there is one more stray capacitance, which is called the junction capacitance. Okay. Junction capacitance, and let me see that if I can have no, that paste option is not there. So what do you mean by this junction capacitance? Maybe without drawing I can maybe show it from here. See here, or what do you mean by junction capacitance? Junction capacitance is basically the PN junction capacitance. So here you can see it is the N plus region, this is the P plus region, right? And you know that any P plus means any PN junction, okay, there will be a depletion region, right? And that this depletion region would generate or would create a capacitance, right? So this region, so I hope you are getting my point. So this N and PN junction, this PN junction would also generate another type of capacitance. And obviously now you can say that this capacitance would not be connected with the gate, but this capacitance is connected between, see, like from source, it is connected from source to body, right? This is a PN junction, and this capacitance, the same thing would also be there on this drain side. It is connected from this drain to body, right? Now I would leave it up to you, like which capacitance you think would impact more here, like this capacitance or this capacitance. Okay, please think of it, and think of it from the bias point of view. How do you bias this source and how do you bias this drain, and what is happening to this PN junction? Okay, so this junction capacitance, I hope then the background is ready. Why do we expect an junction capacitance? So if we have to illustrate it, we can probably do it from this diagram. Let us say that I am just magnifying the drawing. Okay. So let us say that this is a type of that one 3D gate I am drawing, and here is also that this is the gate part. Okay, probably I have to also do an oxide part, because without that this would not help. So this is an oxide part, right? And now we have to plot this drain, right? So, and for this, so I hope you are getting my point, that what I am what I am trying to draw. So this is the drain side. Okay, so this is the drain side and this is the region. So there will be some overlap between the gate and drain. So I am trying to draw it like this. I hope from my drawing it is somewhat clear to you, like what I am trying to draw, right? So this is basically that N plus drain region. The same thing will also be there on the source side. I am not drawing just to save some time, right? This is the overlap region, right? So, and this is the N plus region, right? Okay, and you know that this is gate, right? This is below that green one is oxide. Green one is oxide. Oxide is only one E, not double E. Okay, this is oxide and this is N plus drain. Below that, you always know that it is this P, not P plus, it is this P silicon region. P silicon region. So then obviously there will be one junction and between this P and N, right? Between this P and N. Okay, now if we see, I want to suppose if you want to have to consider in terms of the area to find the capacitance, then also we know that this width we have referred it with W, right? So this is the W width, and say this length, this is the LD. So this is the diffusion length, means the total drain length, physical drain length, right? And this is the depth of the junction, right? PN junction. So let us say that depth is xj. Okay. Then can you tell me quickly what would be the capacitance? If you have understood, I think you should be able to tell me what is the capacitance. Yeah, who can tell? Yeah, Josh, can you tell?
CGCD.
CGCD, which part you were considering, which plane? Okay, just let me also to make these things easy, let me, color this. So I want to find the capacitance for this plane. This is a PN junction plane, right? So tell me the capacitance for this plane. So I'm writing it as C bottom. Please tell the capacitance for this. Say, okay, if you do not know, or if you forgot, like, what is this capacitance? So let us take it between this PN junction, let us take it like Cj. Cj is the capacitance per unit area for this PN junction. Then can I not write W into LD?
Yes, sir.
Capacitance PN junction per unit area, right? Okay. Now what is Cj? Please try to find, okay, from your semiconductor book, what is Cj, and say this doping concentration is given as this is N plus, right? This is Nd. Okay, this is Nd, and here the doping concentration of P silicon is Na. Then find, okay, try to find Cj in terms of Nd, Na. Okay, please do find. I may give some type of problem, some problem like this. Okay, if you have to find it. So you know then what is this C bottom part, but along with that we can also see there are other components would also be present. For example, the capacitance will also be there because of this surface, because of this surface, because of this surface, right? Three side surfaces. Now the question is whether these capacitances will also be like per unit area capacitance will also be Cj. The answer is no, because the doping that you will be used on these sites, that would be higher than this P of this Na. Okay, so what do I mean with this? I wanted to mean that you will also dope this region, right, on these three sides. Okay, on these three sides. I hope that you are getting, like, I cannot draw it here, then it would be difficult to understand. But what I'm saying that here Na is much higher. So if this Na is much higher, then obviously these two capacitances would be different, right? Okay. Then, and you can see this here, this is the component Xj, right? And so it depends on this junction depth. Okay. So the C sidewall capacitances are denoted as C sidewall capacitance. SW is the sidewall capacitance, is denoted as C of sidewall per unit area into xj into w plus 2ld. So please check, is it right to write this CSW in with this? Please check, is this right? Aryan, Yeah, what about Alisha? Seems Aryan is not present.
It looks like right.
Okay, and why do you think there might be some error? You can discuss that. I would be happy.
Again, there's like that oxide overlap over there, right? So that overlap might cause problems with the XJ into LT.
No, no, Alisha, you are doing some mistake here. Please remember that again. I think I told you this junction capacitance. There is no role of this gate capacitance, right? It is we are considering between this gate and between this drain and this body only.
Okay, so then I don't see any major.
Issue, right?
Yes,
Okay.
sir.
So then can I write it like, this CSCJSW dash is the this capacitance, sidewall capacitance per unit area, right? Then simple, right? If you just understand this very basic things, right? It's basically the CSW and then find the area and you have to just find this capacitance, right? So this is the junction capacitance, right? So just give me a minute. I just want to total summarize here. So this is C bottom, which is associated due to the bottom part of this, and the CJSW because of these three sidewalls, because of this, and everything is all these capacitance are rising because of this diffusion, N plus diffusion. So overall, they are called it as C diffusion or diffusion capacitance, right? So C diffusion, then it would be the summation of these two, LD plus this CJSW into W plus 2LD. Now again we have you can see from here I have written here this CJSW because this XJ is a technology parameter. I have just multiplied it this two. So this is basically CSW into XJ. Okay, as XJ is the technology parameter, right? So with this, I think we have discussed the major source of capacitances, right, which are present in a MOSFET, and maybe in tomorrow's class we will start our discussion from here and see how then what will be the total capacitance, okay, or if you consider from the input side, if you consider from the output side, then how the total capacitance would look like. Okay, it's not only the gate capacitance, right? Right, even if you are connecting like something like from this output, for example, if you see for here, like here you can see we have connected an output capacitance CL, but we will see that for this inverter, this CL is not the only load. Okay, there will be some component or some capacitive component from this inverter itself that will be loading itself. So that is called the self-loading. Okay, so we'll see that probably in the next class or next to next class, that how this capacitance from this inverter only will load itself. Okay, so depending on the value of this load capacitance, you have to decide there are a couple of other issues, how can you scale it up or scale it down and to change this delay and all these things. Okay, so we'll see that in the next class. Okay, and remember tomorrow there is a class test as well. The syllabus is like whatever we have discussed till last Tuesday, right? From the beginning. Okay.
So,
Yeah.
so we had a small request. Can this